Hello students, I am Dr. Shilpa Keruda, Associate Professor, Department of ECE, SJBIT. Today I am going to explain the input and output characteristics of a transistor. So this is a common base configuration or common base characteristics. In this above figure, the emitter base junction is forward biased and the collector base junction is reverse biased. The input is applied between emitter and base. The base has as the common terminal. The input voltage is therefore VBE and the input current is IA. The output is taken between collector and base. Therefore, the output voltage is VCB and the output current is IC. Next, we have given the input and input characteristics of a transistor. The input characteristics is always a graph of input current versus input voltage. For the CE configurations, input current is the emitter current and the input voltage is the emitter to base voltage. The input characteristics is applied at a constant output voltage VCB. The input characteristics of a transistor in CB configuration is shown in the above figure. The emitter base voltage is plotted on the x-axis and emitter current is plotted on the y-axis. The input characteristics is identical to the forward VI characteristics of a PN junction diode. After the cut-in voltage, the emitter current increases gradually, but after the cut-in voltage, it increases rapidly with a small increase in the input voltage VEV. The input resistance Ri of the transistor in CB configuration is defined as Ri equals delta VBE by delta IA. As the change in emitter current is very large, for a small change in input voltage, the input resistance is smaller. Next, we have the output characteristics. So, output characteristics is a graph of output current versus output voltage. For the CB configuration, the output current is collector current and the output voltage is collector to the base voltage. The output characteristics is plotted for a constant value of input current. Output characteristics is divided into three regions. So, a transistor can operate in any of the three regions: cutoff region, active region, saturation region. Cutoff region. In cutoff region, both junctions of a transistor are reverse biased. Hence, only a small leakage current flows in the circuit. In the above figure, the regions below the curve for IA equals 0 is called as cutoff region. When input current IA equals 0, the transistor is in off state and the output current IC is equal to ICBO, which is very small in magnitude. Next, active region. In active region, the emitter base junction is forward biased and collector base junction is reverse biased. The collector current is constant and is equal to the emitter current. The dynamic output resistance of the transistor is defined as R0 equals to delta VCB by delta IC. As the change in IC is very small in the active region, the dynamic resistance is larger. Next we have saturation region. Both the junctions are forward biased to operate a transistor in the saturation region. Therefore, a small change in VCB results in a large value of IC current. Next, we have output characteristics. The output characteristics of a transistor in CE configuration. It is a graph of output current versus output voltage. The output characteristics curve is divided into three regions. They are cutoff region, active region, saturation region. Next, active region. In active region, the collector current is beta DC times greater than the base current. Thus, the small input current IP produces a large output current IC. Saturation region. The base junction as well as the collector junction must be forward biased to operate the transistor in its saturation region. When the collector to emitter voltage VC is increased above 0, the collector current IC increases rapidly to a saturation value, depending upon the value of base current. It might be noted that collector current IC reaches to a saturation value when VC is about 0.5 ohms. The dynamic output resistance of a transistor in CE configuration is R0 equals delta VCE by delta IC. Cutoff region. In cutoff region, when base current is 0, collector current is not zero. A small collector current exists called reverse leakage current. Next, common collector configuration. In this common collector configuration, the collector is made common to both input and output. The VBC is input voltage and IB is the input current, whereas VEC is the output voltage and IE is the output current. This configuration is also known as emitter follower configuration. The common collector configuration is used primarily for impedance matching purpose because it has a high input impedance and low output impedance as compared to the CB and CE configurations. Next, we'll have input characteristics. The above figure shows the common character input characteristics. This is quite different from either CB or CE input characteristics. The difference is due to the fact that the input voltage VBC is largely determined by the output voltage VEC. So at a constant VEC, if VBC is increased, VEB reduces. As a result, IB decreases. Next, we have output characteristics. The output characteristics are a plot of the emitter current versus the emitter collector voltage for several constant levels of a base current. The current gain characteristics are IE plotted versus IB at constant VEC voltages. Because IC approximately equals IE, the common collector output and the collector gain characteristics are practically identified to those of the common emitter circuit. DC load line of BJT and biasing circuit. So we know that transistor can operate in any of the three regions, namely active, cutoff and saturation region. To operate the transistor in these regions, the two junctions of a transistor should be forward or reverse bias. In order to do so, we need to connect external DC power supplies with correct polarities and magnitudes. This process is called as a DC biasing of a transistor. DC load line. The DC load line for a transistor circuit is a straight line drawn on the transistor output characteristics. To understand the concept of DC load line, consider the common emitter configuration and the output characteristics. For common emitter circuit, the load line is a graph of collector current versus a collector emitter voltage for a given value of collector resistance and a given supply voltage VCC. The load line shows all corresponding levels of IC and VCE that can exist in a particular circuit. Consider an NPN transistor in CE configuration biased in active region. The DC supply voltage VCC forward biases the base current junction and reverse biases the collector base junction. So from this, we will get the equation here that IC equals minus 1 by RC into VCE plus VCC by RC, which is similar to the equation representing a straight line y equals mx plus c. So by comparison, it is noted that along y-axis we have IC and along x-axis we have VCE with slope of line m equals minus 1 by RC. To consider a straight line, consider two different conditions. Put IC equals 0, then VCE will be equals to VCC. If you put VCE equals 0, then IC equals VCC by RC. From this equation, we can obtain a straight line on the output characteristics curve of the transistor circuit with the two extreme points being VCE IC equals VCC minus VCC RC. Next, Q point or a DC operating point. The term quiescent point means still or inactive. It is a point on the DC load line which identifies the transistor collector current IC and collector emitter voltage VCE when there is no input or signal at the base terminal. The DC load line is a set of infinite number of such operating points and the user or design can choose any point on the DC load line as the operating point. The position of operating point on the load line is dependent on the application of the transistor. If the transistor is being used for amplification purpose, then Q point should be exactly at the center of a load line. to avoid any distortions getting introduced in the amplified AC waveform. Next, we have uh, Q pointer selection. Next, we have this is a effect of emitter resistor. In the above circuit, resistor RE is in a series with the transistor emitter terminal and the supply voltage connected directly to the collector terminal. By applying KVL to the emitter circuit, we get the equation VCC minus VCE minus IERE will be equals to 0. Like simplifying that, we will get IC equals minus 1 by RE into VCA plus VCC by RE. If you put IC equals 0, then VCE equals VCC, and if we put VC equals 0, then IC equals VCC by RE. Those two equations are the DC load line points. Next, we have effect of RE and RC. In this figure here, both emitter and collector resistor RC and RE are present and the total DC load line series with the transistor. Assuming IE nearly equals to IC, applying KVL to collector circuit, VCC minus ICRC minus VCE minus IERE will be equals to 0. Like simplifying that, we will get the equation IC equals minus 1 by RC plus RE into VCE plus VCC by RC plus RE. So next, if you put IC equals 0, then VCE will be equals to VCC, and if you put VCE equals 0, then IC equals VCC by RC plus RE. Thank you.